Hi, this is Ana Doblas and this is another video of the course ECA 513. In this video, we're going to describe the ray bending through a spherical boundary and a lens which consists of two spherical boundaries. We will introduce the lens maker equation that we're going to use for estimating the focal length based on the physical parameter of the lens. And finally, we're going to estimate the image location and height both mathematically and using optical tracing through converging and diverging lenses. So first of all, let me introduce to you or describe or define what a spherical boundary is. A spherical boundary is a spherical interface that is going to have a radius r that is going to separate two media with a different refractive index. And we're going to use the following sign criteria. We're going to define that the radius is positive for convex boundaries, or we're going to use negative radius for concave boundaries. So every time that we are meeting boundaries, so we're going to have a beam emerging for an object point located on the optical axis, and it's gonna meet a straight ray, and we're gonna meet with a angle θ1, and it's gonna meet the spherical boundary at a height y. So the ray is gonna bend until it meets the optical axis at the point P2. We are not changing through the bending, we are not changing the height, but the refractive angle does not only change on the ratio with the two refractive index, but it also is going to change based on the height of the object and the radius of the spherical surface. So this is how we're going to define. We can do optical tracing to find the image in spherical boundaries. But overall, what we're going to define is we're going to have remember that an image is composed with the intersection of two rays, and we can have the three following rays. The first ray is the one that goes parallel to the optical axis, meets the spherical boundary, and then gets reflected with a spherical, with the image focus or the back focal plane. So a difference from the mirror, spherical boundaries have two focus. The front focal, that we don't gonna use the prime, and then the image focal plane or the back focal plane. The purple ray is the one that from the object point is gonna meet the front focal plane. It's gonna pass through the front focal point, meet the spherical boundary, and then go away from the spherical boundary as a parallel ray to the optical axis. The other mirror is the one that it goes through the to the vertex of the spherical boundary without any tilt. So we're just gonna do a straight line that passes from the object point through the vertex of the spherical mirror. So another difference between the spherical boundary and the mirrors is that the design. So in the mirrors, we were saying that the real object images are located on the left side, whereas the virtual object and images were located in the right side. Here, when we are thinking about spherical boundaries and lenses, what we are saying is that left side is the real object and right side is the real image. So we need to take care about where it's located, because that's gonna give us a difference on the sign when we are solving the problem mathematically. So more about it, so we can solve it mathematically. So the image equation is exactly the same as the one from the mirrors, where we were saying that 1 over the distance of the object point plus 1 over the distance of the image point. This is equal to the inverse of the focal length. And we are assuming that the focal length is the same from the front focal point and the back focal point. The difference here is that because the two media has different refractive index, now in the height we're gonna have the difference on the ratio between the two refractive index and then the distances and then the original height of the object. So we are saying that because when we form images, the object plane and the image planes are conjugated. So we're gonna say that the plane at D1 from the vertex of the spherical boundary and the plane at a distance D2 from the vertex of the spherical boundary are conjugated, meaning that there is an image transformation between both of them. So if you want to take a little some look around the equation, you're gonna see that here in front of the height, we know that the height of the image is proportional to the height of the object, and that proportion is what we're gonna call the lateral magnification. And when you see the lateral magnification, you're gonna see that we include the minus sign. So if the lateral magnification is negative, means the case that we are illustrating on the image, that the image arrow is pointing down, so that it's an inverted image. But if the lateral magnification is positive, means that the image is straight. So spherical lenses is just two spherical boundaries together. Every side of every surface, every boundary is gonna have a different radius, and ideally you're gonna have a thickness between them, but we always gonna treat them as a thin lenses, so meaning that the thickness theta is going to 0. And then we're gonna have our refractive index, and usually it's gonna be surrounding a medium. So as any lens, remember that we have the focal length. So here, like that particular case is gonna be the one for converging, but when we are defining a thin lens, that means that any parallel beam is gonna converge to the back focal plane, which is placed at the focal length. So the focal length, it depends on the refractive index of the lens, the refractive index of the surrounding media, and the radius for its surface of the spherical lens. We can simplify this equation if we are assuming that the lens is without air, so the surrounding media is 1. And that way it gets a little simplified. When we are thinking about when we are solving the focal length, we're gonna have the difference between between convergence. So convergence, we're gonna simplify as the edges of the regular arrows, but then diverging, we're gonna have like a different edges. And this is like thin converging and thin diverging lenses. So depending of the radius, the sign, we're gonna have different type of lenses, right? So we're gonna have the biconvex, plano-convex, or positive minuscule lens. Those are all converging lenses. So that means that the focal length is gonna be positive. Where the diverging lenses, the focal length is gonna be the biconvex, the plano-convex, and the negative minuscule lens. And based on the type of lens, the radius are gonna have different sign. So sometimes the problem might tell you what kind of lens it is, and then just give you the magnitude over the radius. So you are the one that needs to take care of the sign. So we're gonna estimate the image through a lens that we're gonna assume that it's a thin lens. So we know that D1 and D2 are conjugated planes. So if we have an object at D1 with a height Y1, we can qualitative estimating the image tracing the rays. So now we're gonna have, again, here is like the 3 rays, the one that goes parallel to the optical axis, and then from the emits the lens, the thin lens, and then goes through the back focal plane. Then we have the ray that goes through the center, to the center of the lens without any distortion, and then the ray that converges to the optical axis through the front focal plane, and then when it meets the lens, leave the lens in a parallel way. And then the intersection, this is gonna be my image location. And then you're gonna kind of draw the arrow. If the arrow is pointing down, that means it's a inverted image. If it points up straight, it's an erect straight image. And because the point of convergence is on the right side of the lens, we're gonna have here this image is gonna be real, and then we have, I think it's roughly the same side. This is kind of like a odd configuration, but it's gonna be inverted. How we gonna do it? So now it's a little more simplified. So we're gonna have the focal length and the distance. This equation is exactly the same. The equation that changes is the one from the height, where we don't have the ratio of the refractive indexes. So it's just the difference on the distances and the height. So here is like me trying to say, like, the ray 1 is the one that goes through the center with no distortion. Then we have a parallel beam until we meet the lens, and then go from the back focal plane. And then we have the other ray. This is the optical tracing for converging lenses. So this is now the one that I'm showing with diverging lens. So on the diverging lens, what we have is the difference is that because the focal length is negative, that means that the f prime, this one, the image focal plane, is located before the lens. And this is really important because for the drawing, the first ray that goes parallel to the optical axis, and then when it meets the lens, needs to go to the kind of like the image focal point, right? But now the image focal point is in this location. The other is the one that goes from the center. That's kind of like pretty straightforward to draw. And then you have there already the point, the intersecting point with the two rays. You can also draw the third ray, which is gonna be the one going to the object focal plane, and when it meets, then you just have a straight. And if you look now, the configuration of the image, so remember that it's on the left side, so image, so now image is located on the left side of the lens, so image is virtual. So when you solve it mathematically, that means that the 2 needs to be negative. And then y2 is gonna be positive, so that means that it's straight. Image same direction as the object. And then the lateral magnification is gonna be smaller than 1, meaning that y2 is smaller than y1, so it's gonna be smaller than object. This is the last slide about spherical lenses and spherical boundaries.